Here's another video to the lecture Intro PDE. In this lecture we present section 4.4. This section concerns the maximum principle. So again, this is quite similar to the Laplace equation. Yeah, we will see that again the mean value property implies a maximum principle. Now, first, before we introduce the maximum principle, we define for any open domain the parabolic cylinder. Yeah, so if we here denote x and t, and we have here some open domain omega, yeah, then the parabolic cylinder is this domain, but important is it contains also this boundary part, yeah. Whereas the other boundary parts belong to the boundary. So this is the boundary. This is the boundary of the parabolic cylinder, but this belongs to the parabolic cylinder, so it doesn't belong to the boundary. Okay, now what is the strong maximum principle? The strong maximum principle, we assume that omega is path connected. This means any two points are connected by a continuous path, and U twice continuously differentiable solution of the heat equation with continuous extensions to the closure. The closure is here the usual closure. If U takes the maximal value inside this parabolic, then U is constant. So the main difference to the proof is for the Laplace equation is that this also allows the points here. So, and the reason is that for xt with x in the interior, with x in omega, yeah, so this is a point here of the heat ball R is for small r contained in the parabolic cylinder. Yeah, so here we have the heat ball. Yeah, because the heat ball is strictly in the past. Yeah, it's contained in this. Okay, now we use the mean value property. So what does this mean? Yeah, let's recall the mean value property. Here we have that this expression here, where this is just 4, this is u. So we use now the mean value property. So let xt element omega t be the maximum of u of u. Okay, then we have u of xt is equal by the mean value property is equal to 1 divided by 4 times r to the power of n u of ys y square over s square dny ds xt r for small r. For small r, yeah, such that this ball is, yeah, with such that this ball is a subset of the parabolic cylinder. Okay, so so this means that yeah, and since the integral, if we insert u equals 1, then gives a then this integral is just 1, so we have u of, so this implies 0 is 1 over 4 Rn integral, and now we just take u of xt minus u of ys, y squared over s squared dny ds. And of course, this is also, by the maximum principle, since this is the maximum, this is for Rn integral absolute value, u of xt minus u of ys absolute value, y squared over s squared dny ds. Sorry. Here, sorry, this factor, of course, we have to correct, This is y minus x squared over s minus t squared. S minus t squared dny ds, and here the same, y minus x squared over s minus t squared dny ds. Okay, and since this is 0, this implies clearly, so this implies u of ys is equal to u of xt, for all yt in the heat pole. Okay, now if we have any other point, if we have any other point here, then we might collect this by a path, and then we choose along this path heat balls, and then we get that this is indeed equal here also. So this also holds, extends to heat balls which cover a path from any point, from the maximum to ys. And so u is constant on the parabolic cylinder, and by continuity also on the closure. So this proves here the strong maximum principle. And again, again this implies the weak maximum principle, like in the same manner as for the Laplace equation, this implies also the weak maximum principle. Okay, what is the weak maximum principle? Again, we have an open and bounded domain. We have a twice differentiable solution of the heat equation, which extends continuously to the closure. Then a maximum of U is taken on the parabolic boundary. Yeah, if it's taken in some point not in the parabolic boundary, then it's constant, and this means a constant in the corresponding connected component. And this means that since the corresponding connected component has some boundary points, this means it is also taken at the boundary. Okay, now of course this maximum principle implies uniqueness of the boundary value problem. Yeah, this is again the same. So what we give for what is our boundary value problem? Yeah, so we have the equation U minus Laplace U is equal to F on the parabolic cylinder. And we give U restricted to the parabolic boundary is given by some function G, and U restricted to omega 0, so initial value is given by H. Yeah, this is now the problem which we want to consider, and then clearly, also two solutions, the difference of two solutions, vanish on the boundary of the parabolic cylinder and by in the parabolic cylinder the homogeneous heat equation. Yeah, so here, if we compare it with this formulation, then clearly, yeah, the parabolic boundary, this is the same as boundary of omega times 0t, and the union with omega bar times 0. So here, so this means we should assume that instead of this, we give the value, we give the value on the boundary of omega. Yeah, here we usually write this as boundary of omega 0t, and there we call the given value G because it's the boundary value of the domain omega. Yeah, so in our picture, maybe I draw now new colors here. Here we have G, and here we have H. Yeah. Here we give the boundary, because this is the boundary of omega, and here this is the initial value. Okay, this is boundary value, and this is initial value. Okay, so now it's clear we have this uniqueness of the boundary value problem, and now we want to now we want to extend to the Cauchy problem. This means if we do the same thing on Rn, yeah, we want also a maximum principle for the Cauchy value problem. But in order to do this, yeah, since this means we do it for omega, so for omega equal to R to the Rn, we need some bound on the growth at infinity. Yeah, more precisely here, this is the growth at infinity, what I mean. Yeah, so we will see that we really need this. Without this assumption, we will construct several solutions of the initial value problem. Okay, so now here, what is the statement? For a bounded and continuous initial value h, let u be a solution of this problem, of the initial value problem, which is bounded here by u on this interval for some constants, a positive constants. Then u is bounded by the supremum of h. Okay, so this is a mistake. Let me remove this mistake. So now I removed this mistake. Okay, so the statement is that then any solution, yeah, of this initial value problem, where we fix this value, which is bounded by such a function. So this means the growth at infinity, if x becomes very large, is not arbitrary. Yeah, it's bounded by some exponent. Yeah, okay, some function. Then the supremum of u is just the supremum of h, of the initial value. So we do this by two different cases. We first consider the case that for a t is smaller than, yeah, proof. So we first assume that for a t is smaller than 1. Yeah, okay. Then there exists epsilon larger than 1, of course, such that for a times t plus epsilon is also smaller than 1, yeah, if this is smaller than 1. Okay, now we introduce this function. Yeah, we look for this function. T plus epsilon minus t, and then n half, sorry, minus n half. Oh, here's again a mistake. Let me call. So I claim that this times the exponential of x minus y squared divided by 4 times t plus epsilon minus t. Yeah, that this is solves, so the equation tx going over t solves homogeneous heat equation. Yeah, and in fact this just follows because this is a multiple of the fundamental solution translated. Yeah, translated by, yeah, let's compare with the fundamental solution. Yeah, the fundamental solution. Here is the fundamental solution. So here with the minus we have exactly this exponent of the this term in the exponent, translated just of course by t plus epsilon and by y. And here we have we have the negative sign, square root of the negative sign, and but this is only a factor. So since this solves heat equation, also this solves heat equation. Yeah, so we indeed get a solution of the heat equation. Yeah, this solves homogeneous heat equation. This is what is just the calculation which we did. Okay, so we know that this solves the heat equation, and then if we subtract from u mu times this equation, then by the weak maximum principle applies. Yeah, the weak maximum principle applies. Now, since our functions u and h are bounded by this exponential and by this inequality, this inequality of course implies that 1 over 4 t plus epsilon is larger than a. This is larger than a. And so this means in particular we have 1 over 4 times t plus epsilon minus t is of course larger than larger or equal 1 over 4 t plus epsilon, and this is larger than a. So if we look at this factor here, this decays slower, because this term here is larger than a, so this decays lower. So this means if we make the radius very large, then this expression here dominates u, because this u decays grows not as fast as this solution. U grows not as fast as this exponential for given t, x minus y squared over 4 t plus epsilon minus t. So this means, and of course exponential, since this is larger, then for large r, so this means for large r, we may always achieve that this negative term here dominates u. We may achieve that this difference, that u minus this difference, so we call it v is then 0 on the boundary of any large balls y r, for r larger than r. Okay, so and this is also the case for the parabolic cylinder of this ball. Sorry, here this is again a mistake. So on the parabolic cylinder corresponding to this ball. Hence, the weak maximum principle implies that this function is smaller or equal than h. Also on the boundary part, so here for this, on this part we have h, but if we make this very large, yeah, then here it's smaller than 0. So we just only get here as the supremum this one, yeah, on the. So we really get that v is smaller than this, yeah, and since this is true for any mu larger than 0, of course the radius depends on the mu, but we might choose the radius as large as we like, and then for any mu we have such a radius such that far outside, here far outside, if we go here far outside, that then this v is on this red part, it's negative, and here it's bounded by the supremum of h. So in this sense we get this estimate, yeah, and since this holds for all mu, we by continuity this also holds for mu, and this implies now the statement for under the assumption that 4at is smaller than 1. Now, if this is larger or equal to 1, then we decompose this, yeah, and we apply then inductively, yeah. If we have this, then we decompose this in small intervals which obey this property, and then we first, so we first have here such an interval, and such. Then we first get this for this interval, but this means as the initial value on the second time, now we have the same estimate and so on. And so inductively we again get this on the whole parabolic cylinder. So this proves the maximum principle for the Cauchy problem. Yeah, so the essential new ingredient is this growth bound, which we have to assume. So now we want also existence and uniqueness of the initial value problem. So for any, we have two statements. For any continuous function, here h, and for any f, inhomogeneous function, which is also continuous, there exists at most one solution of the initial value problem, yeah, now on the whole Rn, which obeys such a growth condition. And if h and small h and f also obey this growth condition, then this unique solution is given by this formula. But one has to be careful. This formula does not necessarily exist for all t's in this closed interval. It might explode at some finite time. Yeah, so this is only true for small values of t. Okay, so then this unique solution is given by this, and it's only defined on some interval up to time t0. Okay, now what is the proof? Also the first statement is clear. Yeah, if we take the difference, then we get homogeneous heat equation. Yeah, the half cancel, and initial value 0. So by the maximum principle for the Cauchy problem, we get that the solutions are equal. Okay, so this is easy. Now we want to show the existence. So we want to show that this function really obeys the growth condition. Yeah? Now we need to show that this function obeys the growth condition. So how we do this? So we first consider t and s which obey this estimate. Yeah, this is, we first consider t and s which obey this estimate. Okay, then we have then we clearly have that this, yeah, this expression here. So let's do the calculation. So we have minus x minus y square over 4 times t minus s. This is of course the same as x minus y square 8 t times t minus s minus x minus y square over 8 times t minus s. Okay, this is clear. Now this here, since we have this estimate here, yeah, if t minus s is smaller or equal to 1 over 16a, yeah, this of course implies, this of course is positive. Yeah? So this implies that that now we put 2a is smaller or equal to 1 over 8 t minus s. And so we replace this here, so with the negative sign, so minus 1/8 of t minus s is larger than minus 2a. Yeah, so sorry, is smaller. Yeah, if we reverse, then this inequality reverses. So we get this expression, and then by the exponential, yeah, then we get that phi, let's recall the formula, phi of x minus y t minus s. This is just given by the exponential of x minus y square over 4 with a minus t minus s, and then we have this factor 4 pi t minus s n half. Okay. Yeah, so we have here we have this factor, and this here we multiply this by these two functions. Then we can estimate this. Yeah, here first by this factor and then by this factor. Yeah, and now we put out here the 2 and replace it by 8, so we get an additional factor n half. Yeah, this cancels of course here with this 8. And now if we multiply this, yeah, minus 2a x square minus and a plus a y square minus 2a x minus y square. Yeah, so what is this? This is of course here, if we multiply this out, how many x square we get? We get here 2 minus 2 is minus 4a x square. How many y squares we have? Here we have minus 2 plus 1 is minus y square. And how many xy we have? Here we have plus 2xy. Yeah, and sorry. So we put out minus a and then 4x squared. And here we have 2 times 2 is also 4. And this is of course the same as minus a 2x minus y square. Yeah, if we multiply this out, then we get exactly this. Sorry, plus and minus. Yeah, okay, so we get this. And so this is just combined combines to this factor, and this remains, and here we have cancelled. Now look at this. Yeah, so we may estimate this here by the inverse of this factor, which is this, the inverse by this factor, which is here this, then this factor, and this here is nothing else but this, where we replace t minus s by 2 times t minus s. Yeah, and now we may estimate. Yeah, now we may estimate if we insert this insert this in the integral. Yeah, if we insert this in the integral, and then we put out yeah, this factor, we move to the left. Yeah, so since we integrate over y, we let this factor be inside, but this factor we may put out and divide and put to the right. So we get that this, so we have e to the minus 2a x squared u of xt is of course the same as integral over Rn. Yeah, here first we assume f is 0, so we only have this integral. Okay, so we have this integral, so this is fx minus y to t minus s, but s is 0 here, so it's just this factor here. Okay, here's again a mistake. I correct this. So I corrected this mistake. Okay, so we have this integral times h of y dny. Now we may estimate this in absolute values. So this is of course smaller, integral over Rn phi of x minus y times t. And now we use this estimate. So we replace t by 2t, 2 to the power n half. And here, of course, we have, sorry, yeah, this factor we don't have yet. Yeah. But now we put this factor in. Yeah. Now we put this factor in. So we have e to the minus 2ax squared u of xt, absolute value, is then smaller. By this estimate, if we multiply with this cancels, so we get integral over Rn phi of x minus y to t, and we have 2 to the power n half and exponential of minus a y squared h of y absolute value dny. And now look at this. Yeah, besides this factor, this is exactly the solution of the initial value problem with initial value, absolute value of this function. So we now of this product here, yeah, this is new initial value. Okay, now we may apply the Cauchy, the maximum principle of the Cauchy problem. So we obtain that this is bounded by the supremum here, this supremum, times this factor, of course. Here we have in addition this factor, and the only other thing is that we have this rescaling of time, but this doesn't matter since this was true for all times. So we really get this estimate here. For non-vanishing f, we get the same estimate for this expression here. If we first integrate over dny, then we have for this integral, we have the same estimate. Here t is only smaller, so we have the same estimate, and so we get this estimate. Yeah, and here, of course, we have to assume that t is in 0t, and t, we made this assumption, yeah, and t is smaller equal to 1 over 16a. So and this is equivalent clearly to t in 0 with t0, with t0 is the minimum of t and 1 over 16a. Yeah, okay, so we define this, and then we get this estimate and also this estimate. So the given u, this now shows, yeah, that the given u really obeys such a growth estimate. Of course with a different a, but this doesn't matter. Yeah? This doesn't matter because we only need any positive constant. So we get a weaker growth estimate, but still a growth estimate of the desired form. So this means we really get a solution of the heat equation with which obeys a bound as described, and so this is a solution. Now what happens if we go further? Of course we might apply this and increase this again and so on, but in any case after finite time the solution might explode, and this we see by this example. Yeah, this again solves the heat equation, and if you look at this, then you see if t goes to infinity, yeah, then for t going to t0, yeah, 1 divided by 4 t0 minus t goes to infinity. So the exponential here goes to infinity. So it does not obey in the limit any such growth condition. Yeah, it does not obey any such. And of course it explodes. So this solution of the heat equation, and clearly if t0 is large enough for t0, it obeys a growth condition. Yeah, but it explodes in finite time. So one really sees that this solution, even this solution, might explode in finite time. Yeah, so okay, here we have, by our arguments, we have this estimate. At least we might move to this estimate. One might improve this and show here this estimate suggests that we have that the time when it explodes can happen earliest at 1 over 4a. Yeah, this is exactly what this exponential, and one really can show that this happens only, yeah, when these arguments might be improved slightly and show that this can only happen if t0 is larger or equal to this time. Yeah, and for this time this solution really shows that this can happen. Okay, now we want to give the promised example, counter example of the uniqueness solution. So we make an ansatz. Yeah, we now construct a homogeneous a solution of the homogeneous heat equation. Yeah? So we write this, if we make this ansatz here, yeah, then we can calculate here this derivative. We can just calculate this derivative, yeah, and we do it in one dimension, so we just get here for the second derivative with respect to x, these two factors, and the powers reduced by 2, so we get this. Now we want to solve that this is 0. We want to solve that this is 0, and this we can easily solve by making this power, this formal power series. Yeah, since we make this formal power series, okay, we only take even powers, and then if we increase the even powers by 1, yeah, then this term cancels always with this term. Yeah, so this is built in such a way that the higher powers of L cancels with the higher time derivatives of this function. So if we make this ansatz, then by this equation, this solves the homogeneous heat equation. Now we choose this function here. We choose this function here and then show that for this function, this power series really converges. So how we do this? First, we solve the derivative. Yeah, for this functions, we write the Elf derivative. Yeah, in order to then estimate now this series, we write the derivative, and that's clear. The derivative, if we take the derivative, we get a polynomial of this form. Yeah, and if we do the calculation, so let's do the calculation. If we calculate g of t times some polynomial p of minus t squared, and if we then take the derivative of this, of course, what we get, yeah, on the one side we get g of t has this expression, so we get minus, this is 2 times 2 t, also the inner derivative is also the, yes, sorry, I forgot. Yeah, we need, of course, we also need this power. So we have t to the power of minus L, some polynomial, PL of t to the power minus 2g of t. Okay, if we do the calculation, yeah, then if we take here, first we take here the derivative, yeah, then we get minus, also the derivative, we get plus 2, then t minus 2's derivative is of course divided by t minus 4, yeah, the t minus, also if we t minus 3, yeah, so this is t minus 3, and this is the inner derivative here, and then we get times PL of t minus 2 times other t minus L g of t. This is the first term if we take derivative here. Now if we take here the derivative, what we get then, there we get again a minus 2. So okay, this time we have a minus 2, yeah, so minus 2 times, again, t over minus 3. Then we have a t over p prime. This is p prime, t minus 2 times g of t. And for the last term, we get a minus L t times minus L plus 1 PL of t minus 2 times g of t. So this 2t, now we set, of course, set is equal to the t minus 2. Yeah? And then we see we get here an extra factor, and one additional factor goes into the L. Yeah, so we indeed get this factor here exactly gives this factor for the if we increase L, we get here an additional negative factor. So this is minus 1 minus 2. Minus 2 is exactly the set. So we get here the set, and then this factor, and this term here gives this term, and this term here gives this term here. Yeah, so they are very similar here. Okay, so we get this recursion relation. Yeah? So this is the recursion relation for this polynomial. Of course, we have P0 is 1. So we see PL has degree L. Yeah? So the PL has degree L, is a polynomial of degree L. If we start with P0 of 1, and then we see P1 is just, there we only have this term. Yeah, so we have 2 yeah, if L is equal 0, then this of course vanishes, so we get the P1 is 2 times Z, and so on. Yeah, by this recursion relation, inductively, PL is uniquely defined. And now we want to estimate. By induction, we want to estimate all the coefficients. Now we claim that the coefficient of PL of Z in front of Z to the power of k is bounded by this constant. Okay, now let's use this relation and translate it to an induction. Yeah, first, if we just increase L by 1, yeah, then this factor 2. Since we have 1 power less, we should take the k, which is the power, we should take it, which is 1 less. Yeah, okay, so since L has here, since we increase the power by 1, we should take here the power by k includes the power here by k minus 1. So this gives this factor here. This gives this factor. Now, since we estimate, we make the minus into a plus. Yeah? So all the absolute values of the coefficients are bounded by this. Yeah? This is the claim. So we say that the absolute values of the coefficients are bounded here by this term. So instead of the minus, we estimate it by a plus. Of course, this is just the old coefficient. And here we take the derivative. This gives an k, and also this decreases, the derivative decreases by 1, and this increases by 1. So again, we get this. Now we collect this. Yeah, of course, we may write L faculty times 7 to the power of L and put this here on this term. Yeah, then here we get an additional factor 2 times k, an additional factor 2 times k. Here's another factor 2, so we get 4k plus L plus 2k. And now we use that k is smaller or equal to L, yeah, since PL has degree L. So all powers of in PL, only powers show up are c to the power of k, where k is smaller or equal to L. So we have k is smaller or equal to L. Now by the induction, now for L plus 1, k is then equal to L plus 1, yeah, by the induction in the next term. So we get for L plus 1, we get by this formula here, we get that this is bounded here. 2k plus 4k is bounded by 6 times L plus 1 plus L is 7, is smaller or equal than 7 times L plus 1. Okay, so we get this term, and this now shows that closes the induction, yeah, because here we get the term for L plus 1. So this closes the induction. Now we estimate this. We call that we have written this formula. So now we estimate this. So this is just this sum here. Yeah, this is just this sum here. K runs from 0 to L, since the polynomial PL, and here we have the coefficients all in front, and the dependence of the coefficients on the K we have written here. So this is the sum. Now here we have L faculty divided by 2L faculty. This is of course the same. Yeah, if we L faculty 2L times 2L plus 1 and so on times 2 times, no, sorry. Also if we have 2 times 4 times and so on 2L, this is of course the same as 2 to the power of L times L faculty. So the even factors in 2L faculty, they cancel with L faculty just by a power of 2L. And then here we collect the odd factors, and the odd factors are also smaller or equal L faculty. So we have that this quotient is of course this here, and this is bounded by this. Now we insert this estimate here. So this means we get rid of these two factors. So, and then we write the 7, and here the 2L is 7 over 2 times x squared over t, over okay, here I forgot in the PL. Yeah, we have this term, so I forgot this term. So let me put in this term. Okay, so now I have this factor, and then I combine, so this power, and this I combine to this estimate. I use here this 2 over L, and this 2, which we put here, and then only 1 over L faculty. And so we have this, and this we just have written as before. Now, of course, this exponential, k equals 0 to infinity, to 1 over g of t, k faculty, times 1 over 2t square, k, this is of course g of t times exponential of 1 over 2t square. But exponential, a g of t is exponential of minus 1 over t square times exponential of 1 over 2t square is of course exponential of minus 1 over 2t square. Yeah, since this plus this gives this. Okay, so we have this expression. Yeah? So we have this expression, and now this is very nice, yeah, because this means this is really bounded. Yeah? This shows that this is bounded, since this is always a finite number, so this is bounded. And if t goes to 0, this dominates this term. So it becomes for any fixed x, if t goes to 0, this dominates, so the whole thing goes to minus infinity, so exponential goes to 0. So it really converges pointwise to 0. So we have constructed a solution of the homogeneous heat equation, which goes to pointwise to 0 if t goes to 0. So we really produced a counterexample, yeah, so we have produced to the uniqueness of the initial value problem. Yeah, we have several solutions of homogeneous heat equation with initial value 0. So this means we may always add this function here to any solution and obtain another solution. But if you look at this term, then you see it doesn't obey the growth condition, yeah, because this factor here becomes arbitrarily large for small t. Yeah, so it doesn't obey this growth condition. Okay, now finally we close this chapter by giving another proof of the uniqueness of the initial value problem by again using an energy functional. Yeah, we define this energy functional and for omega, and which solves homogeneous heat equation and vanishes on the boundary of omega. Then we calculate that the functional is monotonically decreasing. In fact, we calculate the derivative, and we only have to show that the derivative is negative. So clearly here we can put in the time derivative, so we get this expression here. We write out, then we get this. Now since this solves heat equation, we may replace u dot by Laplacian. And now we do a partial integration, where we of course need that u vanishes at the boundary. Yeah. So here we use again that this vanishes at the boundary, and then we can take a partial integration, get a minus and get a square, which is of course smaller or equal to 0. So this is monotonically decreasing. So in particular, if u and gradient u are square integrable, then this vanishes identically, yeah, because of course this functional is larger than 0. If it's monotonically decreasing, then it stays 0, yeah, because it cannot become negative. So if it's initially 0 and monotonically decreasing, then it stays 0. So it stays 0, and this of course means that u is 0. So this is another proof of the uniqueness by the help of this energy functional. Of course we needed also that u vanishes at the boundary of omega. So the solution has to vanish at the boundary of omega, and then the solution is unique. This is a different method which without using the maximum principle. Okay, what we have done today, we first derived a maximum principle from the mean value property for the parabolic cylinder. Also we first derived weak maximum principle, then strong maximum principle, then we improved this and derived some maximum principle on the unbounded domain if we impose an additional growth condition. And then we proved existence and uniqueness of the initial value problem, also if we assume such a growth condition. And then, but we understand that after finite time the solution may blow up, so this growth condition does not guarantee the solution for all times, it only guarantees locally the solution. And this growth condition. Okay, and then we finally presented an example of a non-trivial solution of the homogeneous heat equation, which at t equals 0 converges pointwise to 0. So we see that the initial value problem is in general without a growth condition is not unique. And then finally we gave a different argument which doesn't use the maximum principle but uses an energy function. Thank you.